And we're live. All right, lovely. So everyone that's watching the recording and everyone on the call, thank you so much for joining Compute Over Data Working Group. I believe this is our 9th session, so we're very, very excited to keep the momentum rolling. And on today's session, we have the team from Phala Network. We have Zoe and Shelvin who are going to take us through the product they've been building. Very interesting architecture. I love a lot of things about it and how it's native to their blockchain technologies. Another different type of compute technology. And we also might learn some about the beta program that they're rolling out and how we can get involved as well. So Zoe, if you're ready, I'll go ahead and hand it over to you and let us take us through your content.
Yes, perfect. Hello, everyone. Zoe here from Phala Network. I would like to ask Shelvin if you could share the slides already, if you have access to it. And Shelvin? Can you share the slides already?
Yeah, sure. Let me do that.
Good. Because you just want to give your short, basic overview on the main things that you also know who the team behind Phala Network is. So here today, myself as VP of Growth and Dr. Shelvin, our lead researcher in the team, but also wanted to mention our two co-founders, Marvin and Hang. Both of them have like quite a journey in the Web2 space, but then very early on, very early in 2018, actually realized the power of decentralization and were very motivated to build a decentralized cloud, specifically for the computation part. They know each other, and I think Dr. Shelvin also for quite a while. And they overall got also very, very fascinated by the vision that Gavin Wood puts out while he actually developed Polkadot. So Phala Network is a parachain on Polkadot as well as on Kusama, just to let you know in which ecosystem we are working, and the team is now plus 25 team members. So just to give you this background. And then again, Dr. Shelvin will go into very the details and the technical information. I just want to give you an overview of what kind of cloud we are building and how powerful it is as of now. So Phala Network is really the main for the computation, right? We don't store any data. We work here with Arweave or like Filecoin or IPFS together to actually integrate through APIs, but we are very heavily focused on the CPU computation. So it's a P2P node network, and just wanted to give you some numbers here so you can put it into relation already how big our cloud is that we have built in a decentralized way over the last 3 years. So we have over almost 150,000 virtual CPU globally distributed. So all of these servers are supported, of course, by the community, nothing owned by Phala or the company behind it. And we also have a very high delegation rate. So this is just some numbers to give you this into perspective. And with this, I would already lead over to Dr. Shelvin.
Okay, thank you, Zoe. Yeah, so actually, as Zoe has introduced, actually, we are a decentralized and a permissionless cloud, try to serve as the infrastructure for the Web3 world. And I think one of the very important motivation behind our work is that we have observed that the current decentralized apps is becoming more and more complex. Yeah. So for example, let's use the very popular game, the Stefan, as an example. So like the modern decentralized apps, they should not only need to handle like the on-chain data, like the NFT, like the token part. So I think another very important things is that they need to handle some like the off-chain data, like for example, if you are like a Stefan user, then you need to like buy some equipment like the shoes, and actually the shoes is an NFT and it has some attribute. You can equip it and to gain more profits based on if you have a very good shoes. But when you are really playing the game, that means, for example, you need to like do some I would say that you need to really run, right? And this means the apps, it will need to collect your like the GPS location, like the speed. It needs to do some calculation, and it needs to finally report such data and to finally give you the rewards on chain. So So this means this is the data that decentralized need to process. Yeah. But let's ask for the question is first, can we really do such data processing in the smart contract? And actually, I think the answer from us is no. And also, I think like we will introduce later, right? Like the reality is that these app developers, they will not only they will use the smart contract, they will also like need to use some centralized cloud service, like the service from the AWS and from the Microsoft. And the reason they cannot do that is due to the limitation of the current blockchain or the limitation of the current smart contract. For example, the very typical execution model of the current smart contract is something we call the on-chain execution model. So like the users, they do not see the real workers that back the blockchain. Instead, they for example, when they need to do some calculation, they first submit the transaction and broadcast it to all the blockchain. And then the workers, they will collect the transaction and do the execution for the users. And during this process, actually, for example, like in the Ethereum and in the like other chains, a very important limitation of their network is that not all the workers can be trusted, right? So maybe like here we have 5 workers, 3 of them are good, are honest workers. They really do your calculation, but there are 2 bad workers. For example, this is the bad workers. He deliberately provided the false results. And also there can be some lazy workers. For example, he just ignore any transaction on this chain. He just provides 0 for all the execution. So a very important constraint for this network under the current design is that the honest worker must be the majority of the network. So actually, all the workers, they need to do the duplicated execution to verify that the execution result is right. And the users, they cannot read the result, get the result from any single workers because it can be false. So he have to finally get his result from the block. So because when the block is really appended to the blockchain, that means most of the workers, they have done their verification job. So the result is correct. So this is the current pattern of the smart contract. But this comes the limitation of this. So first is that there is no privacy. And I think, yeah, there is already some privacy related project try to solve this problem. And also I think, yeah, zero knowledge proof can help solve this problem. Yeah, but this is the problem I list for the January blockchain. And the second part is that the computation power, it cannot be scaled because most of the workers, all the workers, they need to do the duplicate computation. They need to verify every block is produced. Yeah. And the third part is that since the users, they have to get the results from blockchain, they need to wait for the latency, the block production interval for each block. So at least like 6 seconds. And if you want more blocks for the finalization, then there should be more times to wait. And also, I think like from the perspective of a general purpose computation, for example, if you try to store the very large data on chain, it can be very, especially like the chain like Ethereum, it can be very expensive to do so. And for example, like the smart contract, you cannot keep a long-lived like network connection from a smart contract because your smart contract can be like executed by different workers. Yeah, and also it's impossible for these workers to delegate the network access for your smart contract. Yeah. Yeah, so this is all the limitations of the current smart contract, and this can explain the reason why our developers, apart from the smart contract part, they still need to rely on the centralized service to do the things that you cannot do in the smart contract. So I think this is a very typical like architecture of a decentralized app, and I think that we have already done a good job because you can see we have decentralized a lot of most of the part of these the apps. For example, we already have decentralized storage here, and I think all the on-chain asset is decentralized. Yeah, but I think the last part to be decentralized is the backend program part. So now they still need to write a backend program and deploy them to the centralized web cloud. But this is the problem we try to solve. And I think the very important specification for the Web3 based backend is first, it needs to be blockchain native. I think the most attractive part from smart contract is the enforced execution of the smart contract. So this implies no trust. So no one can shut down your smart contract or change your logic. So this is, I think, this is the basis for all the the trustless infrastructure. So also we try to support other things you need to achieve in a backend programs, like the low latency response, like the continuous service. For example, you want to do a very heavy, very complex computation in your contract, and it can take 10 minutes to go. And we do not want these computation to be break into different pieces, and each piece is just 6 seconds at most. Yeah. So also we try to, as a backend service, we can see that a backend service, it need to connect to all the other components in this system. Like it need to connect to the storage service to read and store some data. It need to connect to the other chains to read the balance of our users on-chain account. And it need to directly serve the front end, because users may send the request to these servers. And finally, it also needs to connect to the other Web2 services, because you need to, for example, you want to read the price of certain pairs. So this is the last part, the connectivity. We also want our backend programs to have the connectivity to connect to all the components of these decentralized apps. And this is our solution. So first, we have our Phala network, which is a very important infrastructure for this, because it has the computing power, and we have many servers all over the world. And the good part is we all know of them. Yeah. And another part is the fact contract, and fact contract defines how you can use our services, because actually we don't want to rent these hardwares to our users and let them do the setup themselves. So instead, we try to wrap it into a serverless service. So actually, they do not need to care about the underlying hardwares anymore. They can just deploy their programs and to deploy it to any numbers of the workers they want. Yeah. So the first part I will cover is that how we build this computing cloud. Yeah, so I think still the very important feature of it is that first it needs to be permissionless. Is that we want to allow any people who has the hardware to join our network to share their computing power to the users. But on the other hand, actually, we want this cloud to be trustless. Is that we do not trust any one of our workers. So we try to provide the hardware-based promise that our workers cannot to peek at our users' data to try to provide false results. Yeah, so these are the permissionless and the trustless nature are the things we try to provide for our cloud. And now we already have over 17,000 of the nodes all over the world, and all of them are based on the hardware called the secure enclave. So since many people are here, I think at least you have heard the trusted hardware. So yeah, I will also introduce it for brief. So before we go further, I think it's reasonable for us to first look at the limitation of the existing smart contract and understand why there is such limitations. So the most important reason is that any single worker of the current network cannot be trusted. So that means, for example, the privacy problem, the duplicate execution, the block production waiting, all these things is that because that the execution results, single execution result must be verified by all the workers in these chains, and then they can be uploaded to the blockchain. And for these extra functionality, the reason we cannot trust the worker is that we do not know whether they really do that. For example, they may claim that they have already delegated the network access for you, but they can just do not do it. So all these things are caused by the untrusted nature of the workers. So here comes the problem. What if we can make these workers honest? And here, when we say honest, actually it means that all these workers, they will faithfully run the programs we provide to them, and that they will not provide false result to you. Yeah, so this is the honest meaning in our situation. And also, this is why we choose the secure enclave or the trusted execution environments as our solution. I think Phala is not the only team which use the TE as its workers. For example, the recent security network, and secret network, sorry, and the Oasis Lab, they are both the pioneer to use this TE and to combine with the blockchain. But I think the Phala use it in a slightly different way from all these projects, because the other project, they mainly focus on the confidentiality promise from the TE, because TE has a hardware-based encryption chip inside it to encrypt all the memory for you. But actually, from our side, since we are a cloud, confidentiality is also a nice to have features, I would say. And also, it's very important because it protects the data privacy for our users. But actually, for the nature of the cloud, the more important things is that we need to ensure that all the execution of our users' program are correct. So that's why we are relying on the execution integrity promise from the secure enclave. And this means the secure enclave, they will faithfully execute our we released program for it. And yeah, so that's the difference of how Phala used the TE. Yeah. And to ensure this execution integrity, we need to ensure that first, we need to ensure that every one of our workers, they are really running the trusted hardware. They are really running the secure enclave. And another thing we need to ensure that is that they haven't modified the program we have distributed. So, and the program is called the P runtime. It's short for Phala runtime. And actually, to achieve this process, we rely on a process called the remote attestation. And the remote attestation is a very important component of the modern TE solutions. And what it do is that first, in every CPU, like the Intel CPU, it has a secret key inside the CPU during its manufacturing. And also, this means that every CPU, which is verified by the manufacturer, like in this case, the Intel, it has the ability to generate a unique remote attestation report called the I quotes. And it contains all the information we need to know about this hardware and our program status. For example, this report is first verified and certified by the Intel, so we can know that it's really a valid hardware manufacturer from them. And also, it contains the hardware information and the firmware information of this hardware, so we can know that our program is really running inside a trusted hardware. And also, we can know about all the vulnerabilities information about this. For example, like in the Intel report, it will provide something called the security level. And for example, it will tell you under the current firmware version, how many known vulnerabilities are there in your hardware. Yeah, so this is what we can learn from the hardware information. And also, the final part is that we have some information on the program is now executing inside the SGX. So from the code hash, we can know that our program, our P runtime is not modified by any workers, and also it can contain the initial memory layout of your program. So we can also know that the initial state of your program is determined. Yeah, so all these things can ensure that every worker in our network, they are really running the secure enclave hardware, and they are really running the program we have distributed. And with this promise, actually, we can change the previous execution model of the current blockchain. And still, this is the very typical on-chain execution model. But in our case, actually, we turn it into something called the off-chain execution. So first here, actually, we still have some validators in our chains, and actually the consensus is based on the POS. So, but in our case, the validator, they are only responsible for the transaction collection and the block production, but they do not really do the execution. So another very important part in our network is the off-chain workers, and all of them are based on secure enclave. So what these workers do is that first they keep syncing the transaction from blockchain inside our workers, and we have implemented the simple payment verification protocol inside our workers, so it can know that the transaction is received is valid. And during the sync process, all the workers, they are do the execution off-chain, and they keep updates their local states. And finally, a very different thing is that the users, they do not read the execution results on-chain because we do not post the updated states on-chain. They directly read the states from and the results from the workers. So this is what we call the off-chain execution. Yeah, and another part I will not introduce in today's talk is that about our quality of service insurance, because with the previous protocol, actually we can ensure like the security and the privacy of our network, but we cannot ensure that each worker, they provide very good quality services. For example, they may reduce the frequency of their CPU, and they may for example, provide very low the network connection with very low bandwidth. So actually, we have another tokenomic to encourage them to provide high quality services. Yeah, I think until this part, I think if you have any questions, we can first have a short Q&A. So to ensure that I have really introduced the infrastructure of our network well.
Shelvin, I'll just sort of, add to the context that I love the characterization, the framing of the problem, the way you guys have framed the Web3 spec. I love the approach you guys are taking. I think it's very innovative. It's on-chain friendly enough, but it has a lot of extensibility off-chain. Could you say anything about, from the perspective of a, would you call it a miner or a worker? Would they have some spare compute and they would just run your program and it would run in the background? Or what does that experience look like for that group of people?
For our workers, actually, we provide like all these period time, and also we distributed the Phala node for them, because actually in our chains to run as a workers, actually first you need to run a node to keep syncing the to maintain the P2P connection to the blockchain, and also this node, it will keep syncing these transactions into the period time. So, and we packed all these things into a Docker image for them, so our workers, they can easily do all these things with, even if they are not very good operators. So I think to be a workers in our chain is not a very hard job because we have wrapped all these functionalities for them.
I would also like to voice how super cool this is. I know there are a number of folks here exploring T's as well. One question I have is, well, I had several questions. Wes already got to one. I have a second half of that question, which is, how do you allow someone to detect whether or not they have T hardware before download? Or do you just run it, say, you just download the container and then say, oh, we can't detect any T hardware?
This is I think this can be answering here. So actually, for example, when you have downloaded the Phala node and the period time and you run it, you didn't become our worker. So you have to follow the registration protocol. So when you try to register yourself to the blockchain, so the blockchain will require you to provide a remote attestation report. And also it will involve like some random challenge inside it to ensure that you cannot replay the previous one. So this means, so your report here is some user data. So this means the user data will include like the random challenge, and also it will include the generated key inside of the period time. So we can like first we will verify this report, and also we can know your identity, which is identified by these keys.
Yeah. Okay. Makes sense. And then so that you said 17,000 workers. How many of those are any of them yours, or are they all public people joining and contributing?
All these workers are public people with this join.
Okay.
But for example, there is some individuals, but also I think there can be some people who host their own IBCs. So one people he can host like a lot of workers. It's also possible in our network. Yeah.
Got it. And I guess final question is, do you have any case studies or example jobs that you're out there doing? Again, I just think this is the coolest. I'd love to see how people are actually using it.
Yeah, sure. That's what I will cover in the following part, is about fat contract, because the fat contract, by programming the fat contract, then you can use our service. Yeah, so it will come in soon.
Okay, I'll wait. Terrific stuff so far.
There's another question from Path here regarding SGX compatibility. What's your view on some of the vulnerabilities? Yeah, the vulnerabilities, definitely a hot topic that is being discussed right now. Overall for SGX, at the moment, we are only supporting SGX, but it's on the roadmap to expand. We don't want to, rely on only one hardware provider here. But we also created, Dr. Shelvin wrote like a whole article on this SGX vulnerability. So maybe if you want to comment on it directly. Yeah,
I think I can provide some short answer here. So first, yes, we are now only support SGX, and the next thing we do is that we are doing is that we are supporting the SGX 2.0, which has a better performance improvement over the first version of SGX. So another solution already on our list is called the AMD SEV. So yeah, because these two TE solution, I think they are the product ready solutions in the world now. And also I know that there is some open source like solutions, but actually I haven't seen the real products based on them. So when there is really like such products, yes, we will try to explore the possibilities to whether we can support that part. And also another thing, another kind of solution we are looking at is the multi-party computation. Sorry, we cannot use zero knowledge proof because the model is a little different, because you cannot delegate the execution to others under the ZKP. So, but for when the performance of the multi-party computation is improved, also, I also know there is many people working on the hardware on that. Then we are also very glad to use that part, because the MPC, they also like obey our requirements like on the execution integrity and the confidentiality. So it's also can be used. And about the vulnerability, yeah. So I think most of the vulnerability now on SGX is towards the confidentiality, because they try to leak some data from the SGX. But now, to my best knowledge, the integrity of the SGX is still promised. So there is very little. To my best knowledge, there is no thing that can allow you to control the execution integrity inside the SGX. So at least we have the correctness promised, and also our system design. Yeah, we have some key management mechanism to help us to to mitigate this problem, to reduce the attack surface from the attackers. Yeah. If it's okay for Zoe, Zoe can help like to post my articles on that, because yeah, many people ask this, especially for the recent secret network accident. Yeah.
Yeah, it's in the chat.
Yeah, thank you. Yeah, okay. So I think if there is no more, I think we can, yeah, we can go on like how people can use our computing services. Yeah, actually, I think like many other projects, for example, they choose to migrate the EVM, like the Ethereum smart contract inside the SGX. But to our part, I don't think it's a very good idea, because it will, even if it's solved like the privacy problem, it still suffer from all the other things. Like also, I think it can be a little hard to be very complex and the general purpose, like to implement such background program inside the EVM. Yeah, so that's why we try to redo all these things, and we propose our own programming model called the Fat contract. And the good part is that it's very different from the current smart contract, and because it's do the off-chain computation, and every Fat contract is finally deployed to one or more of our workers. So, and the users, they can interact with their with the Fat contract directly by connecting to these workers and send something we call the off-chain query. Yeah, and since the Fat contract itself is executed inside the workers, so for example, if the user they directly interact with it, this means there will be no gas. You just send the request to the Fat contract and you get the results directly. And this also means there is no latency. So, and since this contract is bound to these workers, there is no execution time limit. So it can be executed inside it forever. And also, since all our workers are TE based, and also this contract are executed inside our parent time, inside the secure enclave, so the privacy is also preserved, and also we enable you to do some cool things directly inside our contract. For example, we support the native, we provide the native network support inside Fat contract. Yeah, so I think the good part for our contract is that first it's still deployed through the blockchain. So you need to upload the code in public way inside to our blockchain, and finally the code will be distributed to all the workers, like one or more workers. And I think the initial state of this code and of this contract is determined, because you need to make the code and the instantiate transaction public. But after a contract has been finally deployed to the workers, then you can do all the privacy things, because the following interaction with the contract, no matter you interact with the transaction or like you interact with the off-chain query, all these things will be end-to-end encrypted. So yeah, so then the privacy is preserved. And also we have some mechanism called the key management, which is already covered in my article, is that we preserve some secret key inside our hardware, and this key are used to encrypt the states of these contract, and also it's used to encrypt the traffic to and from this contract. So
sorry,
yeah, please.
Is it okay if I ask a quick question? I just I asked this in the chat, but I'm really fascinated how you allow for arbitrary network egress.
Mm-hmm.
Because obviously that could be, you could just create a bot network, and I was curious how you attack that.
First, actually, since the T itself, it's native, it provides native support for networks. So also we export such interface to this contract. And I think a very important question here is that how we can ensure that these workers, they are not monitoring the traffic in and out this contract. And answer is, first, there is some certificates distributed with the parent time. So actually the workers, they cannot inject their own certificates. So also actually, although we say the HTTP support, but in the real case, we still encourage people to do to send the HTTPS request. So this means no one can see your interaction with the website. And finally, how we can ensure that these workers, they are not block the traffic from the contract, then this will fall back to our tokenomic, because we have a heartbeat check for them to ensure that their network service is really good. So yeah, so by combining this part, you can safely use the network support inside the contract directly.
I'm asking a slightly different question, if that's okay. So you have 17,000 workers. If I wanted to DDoS the White House's website, I could have them all make 1,000 queries per second against the website, and that would take it down. How do you prevent that? Or is network access only between your scheduling node, your scheduling cloud, and the worker nodes?
Oh, this is a very good question. So yes, so first actually to prevent the DOS attack, I would say that you will need a load balance before all these workers. So these load balance need to distribute the traffic to all these workers. And but I think this means actually the Phala network itself, we do not provide the DOS defense program, but actually we just provide the workers. But I think these workers, how you manage this worker, how you distribute this traffic evenly to all these workers is another question, which should be solved by the current front end solution. So I'm not sure whether I have.
Sorry, that was great. I couldn't find the unmute. Thanks so much.
Yeah, thank you. Okay, I can then I can continue. Yeah, so let's compare the on-chain smart contract with our off-chain version. So the first is on-chain smart contract. They are really deployed to the blockchain, and for example, maybe any one of the workers may be lucky enough to be choose to execute it for one block. But in our case, actually, the contract is deployed to one or more off-chain workers, and they are there, so they are bound to them. And the second part is how we store these states. The answer is that we do not store the states, because since our workers, they are trusted, and also we have all these transactions ordered and stored on chain. So any one of these workers, if it's chosen by our it's choose from the on-chain governors, then it will be shared the key to decrypt these encrypted transaction, and it will replay all the historical transaction to get the final states. So, and this means the latest states, they are only available inside our workers' memory. And actually, so this means first the user, they can still send the transaction on chain, and our worker, they will sync these things back to the execution for them. And also they can directly send the off-chain queries to these workers to get these queries, you can do some calculation in it. And also actually you can use this query to read the latest states from the chain. So both these things are okay. And the last part is that we are not only support the on-chain data operation, which just the update of your balance like this, and also we support the off-chain operation, which is very unique to us. So you can do HTTP request. We have the random number generator inside the hardware. And also we provide some volatile cache inside our workers' memory for you to store some data. And also you can use the HTTP request to persistent your data on the solution like the Filecoin. Yeah. So actually our contract, it's do not try to replace or any existing smart contract, because I think, for example, there is no meaning to implement ERC20 contract inside the Fed contract, because the current smart contract can do a very good job, no matter the Ethereum or the Polygon. They all do very good job by executing the current smart contract. But for example, if you try to I think the Fat contract and the Phala network, we meant to replace like the AWS and like the Amazon Lambda. So this is the things we try to do. So also I will show later is that how we enable people like to connect the smart contract to the Fat contract. Yeah, here comes some use case. I think a very interesting use case is that how Fat contract can interact with other chains, with other smart contracts. Since we have the HTTP request and since we have the privacy promise inside it, the things we do is that first you can generate any account of other chains inside the Fat contract directly. For example, I generate an Ethereum account inside the Fat contract, and then you can transfer some tokens, a gas fee to it, to this account, and this account just serve as the gas fee account for you. And then we directly connect to the RPC node of our target chain. So no matter it's Ethereum, actually we have already implemented the support for the EVM compatible chains and for the substrate chains. So this means our contract, they can directly interact with this RPC node, and it will like construct the transaction inside our contract. It will sign it with your gas fee account, and then it sends the transaction to this RPC node directly. So this is how we do the cross-chain interactions. And I think actually we have implemented some wrapper on it because we want to enable that, for example, an Ethereum contract, it can send some requests, and our contract will monitor this request and do the responsible and push the response directly to the chains, to this contract. And this is how we achieve it. And we use the BSC as an example. And here we see a very simple like price feed oracle here. So first we need to deploy some contract called the anchor contract in our target chains. For example, it's just used to store like all the requests from these smart contract. For example, one smart contract will request the price of BTC USDT pair, and another it will request the price for the BTC ETH pair, and the anchor contract will store all these requests in a queue. Then our contract can directly read the contract state, use the HTTP request. So it will know that there is such kind of price feed request here, and then it's read the price from the Binance, so it can get the result directly, and also you can do the JSON result parsing inside our contract directly, so it will know the price. And the final thing is that it constructs the cross-chain transaction directly and send it to the RPC node. So finally, this price come to this target program. So I think, target smart contract. So this is our way to do the cross-chain operation. And there is a simple demo for it. Yeah. So this is the BSC mainnet. And like here we can, contract can require the price for the trading pair, like BTC and USDT. Yeah, and this transaction is finally packed and finalized, and then we can, yeah, you can see how these requests look like. So first, we give it an index. So this is very important because all our Fat contract it can run on all these multiple workers concurrently. So we do not want like this request to be processed like duplicated process. So we give it a unique index to mark it, so we can know that we only process the request of each index once. Yeah, and the request is just encoded, and then this is our contract. Since this is a demo, we just run a local testnet to show its case. Yeah, and the things it do is that it first read the transaction, read the contract in the BSC, and delegate the request and send the transaction back. Yeah, we can see that this transaction has been submitted back to the BSC, and we can check it in this Explorer. Yeah, so actually this transaction is directly constructed inside fact contract. Yeah, and it has the request ID, like the pair and the price. So yeah, so this such information can be directly processed by the smart contract. Okay. Actually, I think with such connectivity, actually we can use it to connect to many different services and try to implement some application which has never to be implemented before. So another library we have provided for our developers is called the Pink S3. And actually it's a library to enable our fact contract to directly interact with any S3 API compatible services. For example, we have the Foreverland, which it can be backed by the Filecoin, and it provides the S3 API for this service. And actually, we can generate a key inside our contract directly, and this key can be used to encrypt the user's data. And also, we can we can do the encryption for our users. We can do the upload for our users. So with just one simple fact contract, we can turn any public storage service into a trusted or encrypted storage service. So I think there is more possibilities for us to explore because, yeah, just use our best imagination. And the last questions I want to answer is how people pay for our service. So actually, we adopt the stake to compute model. And this means, for example, by staking our token, which is called the FAR, by staking the FAR, you can get the proportional computing power from our network. So for example, if you stake 10% of FAR, then it means you can deploy a contract to 10% of the workers in our network. And then they can do the execution for you. And once you do not need our service anymore, you can unstake token to get your token back. So this means there is no fee for the execution of your contract. But I would say for them, if you want to store some data to our chain, you will still be charged by the gas fee, just like what it is in the Ethereum ecosystem. And now we are already launched our closed beta test for the fact contract. And the next step is that we will release the fact contract support on our mainnet. Okay, yeah, and here is some link I provide to it contain the Oracle and the workshop and also some inspection to our fact contract and to our chains. So you are very welcome to follow our Twitter or join our Discord for further introduction. Yeah, and that is from my side. Yeah, thank you.
Fantastic. Thank you guys so much for the content. This is incredibly interesting just to see the different dimensions of how you guys are building this out. The economics model is very interesting as well. I have a couple follow-up questions as well, but I'll just pause to see if anybody else on the call has other questions. Give them a little bit of opportunity to chime in if they have any.
It was a lot of content, right? And thank you again, Wes, for giving us the whole hour. I know you said it in the beginning, it's usually 10 or 20 minutes, right, per project. So we had a little benefit here today.
Yes, and it worked out well because all the topics you guys are discussing are different things that different groups are trying to figure out within our own projects. One technical question I had as a follow-up is, within the host that's doing the computation, they're going to run the Docker image for the Phala worker, and that's going to manage all the TEE and all this. Is there any safety precaution in there to say, if I run my compute job, to prevent it from getting access to that worker's machine and finding out what else is going on in the worker's machine? Are there any kind of hypervisor limitations, or is that just the nature of the TE environment, that whatever job I run deploying on a fat contract, it would not get access to that miner's machine?
Actually now, first the fat contract is finally compiled to the WASM, and all the runtime we have is implemented inside our P runtime. So actually the things you can do in a contract is limited by our runtime. So now we expose something like just the thing I have mentioned, like the network access and like some random generation because people want it, and also some cache, some storage like this. Yeah, but I think the fat contract is still very new. It's a very new product, so still we are very open to to hear the requirements from our users. For example, if you have something, for example, some functionality you want for the fat contract, we are still open to to add more functionality to it.
Very good. And then Zoe, one last question might be, if folks want to get their hands, they want to get involved in the work you guys are doing, or if they want to reach out to you, do you recommend any areas we should funnel folks to get in touch with you guys?
Yeah, maybe we can share the deck afterwards to all the participants, or you could distribute it, and there we have all the links. So just joining our Discord directly, and happy to leave our emails also if you want to reach out to a more direct contact. And yeah, perfect. Shelvin is joining them, sharing them already, the slides here. But we are also, as Dr. Shelvin said, launching Fat Contract on a mainnet next year. We have our closed beta open now. If you're just interested in maybe joining there as an individual, you still have some time this week or next week to send an application. And yeah, and then we are also, of course, working on a grants program, right, to support builders actually using Fat Contract, and maybe even directly with Filecoin or West to have a joint initiative. But this is just for you guys to know that we really want to incentivize everyone to actually use, of course, the tools, and then provide the benefit for your projects and for the network overall.
Very good. We'll make sure to add all these follow-up notes in the Compute Over Data Working Group Slack channel, so that anybody that comes in here after the fact can get access to all this good information, and they can get connected with you guys directly.
Cool. We should join that too. I have the invite open, yeah. And then we can all connect there offline. Cool.
Lovely. All right. Well, unless anyone else has any questions, we'll let you guys run. Thank you so much for the content. This was lovely, and more to come.
Perfect.
All right.
Thank you, everyone.
Thanks, guys.
Thank you.
Take care.
Bye-bye.